Technology is reshaping the world faster than ever, and artificial intelligence-based brain-computer interface helps you make sense of it. We will focus on what it says about classification and features. Stay with me, the best part is near the end. Chapter 1, Remington. 830 total 4700 Fig. Example of EEG signals of sleep stages. Transformation techniques. EEG signals are considered to be complex, non-stationary, and nonlinear. Due to this, analysis of raw EEG signals is very difficult. A signal is transformed to other domain for finding the representative information. A signal in time domain can be transformed to frequency domain, analytic form, and time frequency representation. Analysis of non-stationary signals in time frequency domain has outperformed conventional time domain and frequency domain approaches. 57. Hence, for TFD methods, namely STFT, CWT, ZAM, and SPWVD are employed in this methodology. TFD is defined as a technique that is used to represent the spectral variations, frequency and energy, of a signal with respect to time. The details of these are discussed later. Short-time Fourier transform STFT is a modified version of FFT. It can be viewed as a block that partitions the signal and independently applies FFT to each block. The signal is partitioned by taking off a part of the time domain signal with the help of windowing function. Later, FFT is applied to the partitioned portion to identify different representative characteristics of the signal. The TFD of an input signal S(T) is defined as follows: 49, where P(T) is the window function. The spectrogram of a signal is a magnitude squared function of STFT and represented as spectrogram equals S(T)F(2). The type and length of a window must be same. In addition, a signal is assumed to be stationary in the duration of window. STFT can be picturized as symmetric bandpass filters equally spaced in frequency. Continuous wavelet transform. The STFT provides the signals that can be seen as localized in Fourier domain in the form of some combination of cosine and sine signals having infinite length. This is why some localized time domain information is lost. Wavelets are used as combinations of small oscillatory functions as these are highly localized in time. The CWT functions are used to produce Fourier space as well as localized real space which is scaled and shifted, and these versions become as time-localized mother wavelet. The CWT also maps the TFD information in order to get good time and frequency localization. The CWT of a signal S(T) can be expressed as in Ref. 49, where the scaled and shifted basis wavelet function, T, is denoted by the parameters and denote the scaling and shifting variables. By adjusting the scaling and shifting variables, the spread and the shift of time domain signals can be regulated and localized. Therefore, we can see CWT as linear combination of frequency-varying bandpass filters. The window is used to analyze the lower frequency components of the signal, having larger window size or high-frequency analysis made using low-sized window. This method is especially advantageous regarding accurate time-frequency distribution and redundancy issues. Joe-Atlas-Marks distribution. ZAM distribution is another one such technique for the representation of TFD. ZAM is also known as a cone-shaped kernel. The advantage of the ZAM is that finite time support is maintained in the time dimension along with an enhanced resolution in the frequency dimension. The advantage of ZAM is that the crossterms in time domain are smoothed out. A generalized TFD of an input signal S, T, and the kernel required to compute ZAM are denoted as follows: 58, where T is the time frequency representation kernel, 1, T is the scaling function to be specified during runtime, is the running time, is the running frequency, T is the position variable, A is the constant scaling variable, and S, T, denotes the complex conjugate. The larger length window function captures low-frequency details, while a smaller length window captures high-frequency resolution of the signal. Smoothed pseudo-Wignerville distribution, SPWVD. The SPWVD is seen as very efficient method used for representing the signal energy over time frequency. The transformation produced by CWT and STFT mainly suffers from localization issue that is associated with time frequency. In addition, a crossterm in the time frequency domain is unnecessarily introduced. The TFD suggested by ZAM attempts to address the challenges related to localization, and also the crossterm is reduced in time domain. Nevertheless, the window having smaller size helps to obtain satisfactory level of localization, but at the expenses of poor frequency resolution. This is overcome by the introduction of a crossterm reduction window in frequency domain by SPWVD. The TFD of an input signal S, T, is obtained by SPWVD 5961, where G, T, is the time domain crossterm reduction window, U, F, is frequency domain crossterm reduction window, and FCY, T, F, is the Wignerville distribution. SPWVD has an option to select the type and the length of the window independently. Time frequency distribution obtained by using transformation techniques is shown in Fig. Fig. 3AD represents the TFD obtained by SPWVD, STFT, CWT, and ZAM, respectively. As evident from the figure, TFD of SPWVD provides the highest insight of the signal, followed by ZAM and CWT, and the worst resolution of sleep signals is provided by STFT. In addition, SPWVD-based CNN feature extraction and classification have been used previously for detection of emotions and schizophrenia. 6062. Fig. Example of time frequency distribution of sleep signal: A. SPWVD, B. STFT, SC, CWT, and D. ZAM. Convolutional neural network, CNN. An extensive and systematic analysis is required for appropriate extraction, selection, and classification of distinct features in the classification or its application. There are numerous conventional methods, which are used for the purpose, but the methods suffer with many problems such as tuning of several multiple parameters and more training time. In addition, the methods have more computational complexity and are prone to human errors. The CNN is reported as promising method that has ability to address the issues in conventional methods for classification. The classification including feature extraction and selection becomes much automated with the introduction of CNN due to the convolution operations which are integral parts of CNN. The CNN is an extension of the machine learning family and composed of self-optimized neurons. It is designed to work with images by taking into the configurable structure and special input into account. In recent years, CNN has been used in various disciplines for object detection, edge detection, fault detection, etc. CNN is applied to various applications of biomedical informatics including drowsiness detection and motor classification, seizure classification. 4951. CNN architecture is inspired by the visual perception mechanism of the living creatures. The features are extracted and classified with interconnected multilayer neurons trained rigorously. The previously learned knowledge of preceding layer is used by these self-optimized neurons. The knowledge acquired by the system assists in training one task and reusing the same for other tasks. The CNN generally contains an input layer, an output layer, and hidden layers. The hidden layer can be visualized as combination of layers for convolution, pooling, fully connected operation, and classification. The components of hidden layer are discussed as follows. 63. Convolutional layer. This is the heart and core building block of CNN. Convolutional layer, CL, uses learnable filters or kernel functions. This kernel is moved along the length and convolved with the part of the input image. Each spatial dimension of learnable filters is convolved to find the representative information. The two-dimensional convolution operation is expressed as follows, where X is the portion of the image and Y is the kernel. Zero padding, Z, is used to keep the original size of the image. A stride, P, is used to move the kernel with a fixed pixel. The output volume, L0 B0 F0, for an image with a dimension LC, BC, and FC, can be expressed as follows, where LC is the width, BC is the length, and FC is the number of channels of an image. The filter is denoted by F0 with size K. The activation function is used to increase the nonlinearity in the network. The rectified linear unit, ReLU, is the most common activation function. Pooling layer. The CL layer is followed by polling layer, which is also called a subsampling layer. The main aim of using the pooling layer, PL, is to address the dimensionality probe, and thus, this layer reduces the dimensionality of the feature maps provided by CL layer. This is done by using the concept of downsampling, and the feature maps are reduced. One important point here is noteworthy that output and input feature maps are not affected by the downsampling process. The feature map after downsampling, as reduced feature map, is represented as follows, where additive and multiplicative constants are denoted by DLM and ELM, and downsampling operation is represented by down. Fully connected layer. The PL is succeeded by a fully connected FC layer. The downsampled two-dimensional feature maps are converted to one dimension with a feed-forward neural network. These one-dimensional deep features are then given to the classification layer. The classification layer assigns the score to each object of a class. These scores are then converted to probabilities with the help of some algorithms. Finally, a voting scheme is used to assign a class to an object with the highest probabilities. The steps involved in feature extraction and classification of images are shown in Fig. Users can use these elements of the hidden layer to build a convolutional neural network. The number of components of a hidden layer can be added or deleted until the desired performance is obtained. Besides, there is no standardized CNN available for the diagnosis of brain abnormalities. Now, several pre-trained CNN architectures and models are available having multiple number of CL layers. These types of deep network models can handle huge number of learning attributes, and thus, both computational complexity and computational time are increased. Though, probability of performance success of CNN in many cases becomes bleak. So, the network having less complexity and adaptive in nature can overcome the CNN issues. The current literature suggests that CNN development is taking place at fast-paced CNN, 64-65. To deal with these challenges, we have used an adaptive CNN in this chapter, which has 4 convolutional layers, 2 pooling layers, and 2 fully connected layers. In the first 2 convolutional layers, 96 and 32 number of filters, each of size 77 and 55, respectively, were used. The third and fourth CL layers have 32 and 16 filters, and each filter is having a size of 33. A 50% additive downsampling operation is used to reduce the dimensionality of output maps. The ReLU activation function is used to increase the nonlinearity in the network. The 2 fully connected layers composed of 500 and 128 hidden neurons, respectively. The detailed working of the proposed CNN is shown in Fig. The efficacy of the proposed ACNN is compared with the benchmark pre-trained network. The pre-trained AlexNet, VGG16, and ResNet 50 are used for performance comparison. The detailed descriptions of these networks are available in Ref. Fig. Feature extraction and classification using CNN. Fig. Proposed adaptive convolutional neural network for sleep stage classification. Results: the R&K and AASM standards primarily divide the sleep stages based on scoring. The standards proposed by R&K says epochs of sleep annotated as any one of AS, S1, S2, S3, S4, and REM, respectively. On the other hand, AASM annotates the SWS state as a combination of S3 and S4 stages, while remaining stages are maintained the same. The proposed methodology aims to classify a different sleep stage, 2 class to 6 class. The formation of 2 classes is accomplished by combining S1, S4 and REM stage as sleep class while others as. In 3-class problem, AS, REM, and NREM, a combination of S1, S4, are considered. For class problem is defined as SHS, S1 and S2, SWS, S3 and S4, and REM. 5 and 6 class problems are maintained as per R&K and AASM standards. The details of class formation are shown in table. Table formulation of multi-class sleep stages. Know of class formation 2 awake sleep, S1, S2, S3, S4 and REM, 3 awake. Chapter 2, Remington. A common experimental platform is maintained for transforming the signals into TFD. A non-overlapping Hamming window and 256 points FFT are used to obtain the spectrogram using STFT. The Morse wavelet is used to transform a signal into a scalegram by CWT. To obtain the time-frequency representation using ZAM, Kaiser's window of length 63 is used. In SPWVD, Kaiser window of length 63 is used to reduce the crossterm in the time-frequency domain. The problems of low resolution and high memory can be introduced due to the selection of smaller and larger window sizes. Hence, a medium-length window is selected empirically. The spectrograms, scalograms, and time-frequency representations obtained with STFT, CWT, ZAM, and SPWVD are resized before applying to CNNs. AlexNet and ACNN take input with an image of size 224x24, while the images taken by VGG16 and ResNet 50 are of size 227x227, respectively. The resized images are then given as input to CNNs. The hyperparameters of every CNN are maintained uniform. 75% of the input data is used for training while the remaining is used for testing and validation. The batch size and learning rate are selected empirically to 32 and, respectively. The learning rate of weights and bias is kept at 20, and number of epochs is set to 10. The learning rate of weights is scaled by Atom Optimizer. Table shows the classification accuracy provided by ACNN, AlexNet, VGG16, and ResNet 50 using spectrograms. Classification accuracy with AS and sleep class is 100% for ACNN, AlexNet, VGG16, and ResNet. An accuracy of percent, and percent is obtained for AS, NREM, and REM classification using ACNN, AlexNet, VGG16, and ResNet 50. The AS, SHS, SWS, and REM classification has an accuracy of percent, and percent for ACNN, AlexNet, VGG16, and ResNet 50. Classification accuracy of AS, S1, S2, SWS, and REM class is percent, and percent, while, for 6 class, accuracy is percent, and percent using ACNN, AlexNet, VGG16, and ResNet 50. The average accuracy with ACNN, AlexNet, VGG16, and ResNet 50 using spectrogram is percent, and percent, respectively. The classification accuracy obtained with a scalegram technique is shown in table. The two-class classification shows an ideal response with 100% accuracy for ACNN, AlexNet, VGG16, and ResNet 50. Table accuracy score of sleep stages using spectrogram. Classes. Chapter 3, VGG16. ResNet 52 100 billion 100 million 100,000 103,456 average accuracy of percent, and percent is for 3, 4, 5, and 6 class using ACNN. AlexNet provides an accuracy of percent, and percent, while accuracy of percent, and percent for 3, 4, 5, and 6 class. ResNet 50 produces an accuracy of percent, and percent for 3, 4, 5, and 6 class. Average accuracy performance given by ACNN, AlexNet, VGG16, and ResNet 50 is percent, and percent, respectively. Classification accuracy provided by TFD of ZAM is shown in table. The perfect classification is obtained in case of two-class classification using all the CNNs. Accuracy obtained by AlexNet, VGG16, and ResNet for three-class classification is percent, and percent, while for four-class, accuracy is percent, and percent, respectively. Accuracy obtained for five-class classification is percent, and percent, and an accuracy of percent, and percent is obtained for 6-class using ACNN, AlexNet, VGG16, and ResNet 50. Average accuracy produced by ACNN, AlexNet, VGG16, and ResNet 50 using TFD of ZAM is percent, and percent. Table accuracy score of sleep stages using time-frequency distribution of ZAM. Classes. Chapter 4, VGG16. ResNet 52 100 billion 100 million 100,000 103,456 average. Finally, the accuracy of TFD obtained using SPWVD is shown in table. The accuracy provided by ACNN is 100% for 2, 3, and 4 class, while for 5 and 6 classes, classification accuracy is percent and percent. AlexNet, VGG16, and ResNet 50 provide an accuracy of 100% for 2 class, percent, and 100% for 3 class, percent, percent, and percent for class classification, and percent, percent, and percent for 5 class classification, while classification accuracy provided with 6 class is percent, percent, and percent, respectively. Average classification accuracy for TFD of SPWVD using ACNN, AlexNet, VGG16, and ResNet 50 is percent, 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 and percent. The results of tables show that the distinguishable information provided by TFD of SPWVD is superior to other transformation techniques. The second best is ZAM, followed by CWT and STFT. In most cases, classification accuracy provided by ACNN is higher than that of the other CNNs. The results of tables prove the superiority of the proposed ACNN over AlexNet, VGG16, and ResNet 50. Hence, the idea of the proposed adaptive convolutional neural network is justified. Pictorial representation of the classification accuracy for each iteration using ACNN is shown in Fig. The combination of SPWVD and ACNN is highest over other transformation techniques and pre-trained CNNs. Table accuracy score of sleep stages using time-frequency distribution of SPWVD. Classes. Chapter 5, VGG16. ResNet 52 100 billion 100 million 100,000 103 100 104 105 6 average Fig. Pictorial representation of accuracy using ACNN. To get more insight into the proposed method, 6 performance parameters, namely accuracy, ACC, sensitivity, SEN, specificity, SPE, Cohen's kappa, kappa, Matthews correlation coefficient, MCC, and F1 score, F1, are evaluated. Table represents the performance parameters obtained using SPWVD and ACNN. As evident from the table, the performance obtained for binary, 3, and 4 class is ideal. The ACC, SEN, SPE, and MCC are obtained as 100%, while kappa and F1 measure are 1. ACC, SEN, SPE, kappa, MCC, and F1 is percent, 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 and percent for 5 class, while with 6 class, the parameters are percent, 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 and, respectively. The average value of these performance parameters is percent, 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 and. The results of table prove the efficacy of the proposed method over pre-trained AlexNet, VGG16, and ResNet 50. Table performance parameters of ACNN using SPWVD. Classes ACC SEN SPE kappa MCC. Chapter 6, F1. 2 100 million 100,000 101 101 3 100 million 100,000 101 101 4 100 million 100,000 101 101 5 6 average. Discussion in this section. The superiority of the proposed method over other existing state-of-the-art is proved by comparing the performances. Performance goes along the methods used for analysis, features, classification techniques, and performance parameters as shown in table. The classification of 5 and 6 sleep stages with its accuracy and kappa values is presented. The method proposed by Peeker and Ref. 9 extracted nonlinear features and classified them with CVNN. The accuracy obtained in Ref. 9 for 5 and 6 sleep stages is percent and percent while kappa is and. The FFT, DFT, and STFT-based methods in Refs. 1215 have an accuracy in the range of 61% for R&K standards, while with AASM standards accuracy falls in the range of 76%–86%. In 1922, BPF-based method is proposed for sleep stage classification. The accuracy obtained with 6 stages is %, while the highest accuracy obtained in accordance with AASM standards is % and kappa is. Methods based on EMD and its modified versions have been used in refs. The accuracy obtained with R&K standards is between 86% and 88%, while the accuracy with AASM standards is in the range of 83%–91%. In refs 3638, TQWT has been used for the automatic classification of sleep stages. The highest accuracy obtained with 5 and 6 stages is % and %, while the maximum value of kappa is and, respectively. The highest classification accuracy obtained for wavelet-based methods in refs 28–2935 is % for AASM and % for R&K standard. Sharma et al. 32 used wavelet filter banks to evaluate log energy, fractal dimension, and entropy features. These features have been classified with SVM for accuracy of % and % for 5 and 6 stages. In Ref. 24, RF classifier has classified nonlinear features extracted from the bands of IIR-BPF with an accuracy of % for R&K standard. Features extracted by segmentation and graph visibility in refs 1842 have been classified using a structural graph and SVM. The method in Ref. 18 has an accuracy of % and kappa for R&K standard, and the method in Ref. 42 has an accuracy of % and % for AASM and R&K standards. Histograms have been classified using MCLS-SVM by Bajaj et al. In Ref. 40, which have an accuracy of % and % for 5 and 6 sleep stages, respectively. Recently, Tarun et al. In Ref. 39 classified the features extracted from OFOT using EBT. This method has proved to be % and % effective for the classification of 5 and 6 sleep stages and kappa of. As evident from the table, classification accuracy provided by these methods in accordance with R&K and AASM standards lies in the range of 61%, 96% and 77%, 96%. The value of kappa is in the range of for AASM and R&K standards. In this chapter, adaptive CNN has been used for automatic extraction of features and used the features for their classification exploiting the time-frequency distribution of features. The value of accuracy with 5 and 6-stage classification is % and %, respectively, whereas the values are and, respectively, for kappa. We have achieved a considerable amount of improvement in terms of classification accuracy. We can also see in table that the proposed method has proved to be outperforming than other existing methods for classification purpose. Table comparison report of the proposed method over existing state-of-the-art. Research work method used features classification technique performance parameters R&K STD. AASM STD. Peaker 9 Nonlinear features. Chapter 7 CNN. ACC % kappa % Conclusions. In this chapter, we have explored automated extraction of features from EEG signals using adaptive CNN model and classified the features into multi-class sleep stages utilizing the data from single EEG channel. Time-frequency distribution has resulted satisfactory signal analysis with respect to both the time and the frequency. The transformation techniques play a very important role in extracting the most suitable and useful information from EEG signals. The smooth pseudo-Wignerville distribution produced excellent signal resolution because of the fact that the time-frequency crossterm was reduced. The adaptive CNN provides improvement in distinction and clear differentiation of sleep stages with reduced complexity. The evolutionary combination of time-frequency distribution of smoothed pseudo-Wignerville distribution and adaptive CNN helped to obtain good values of accuracy as percent, sensitivity, specificity, Matthews correlation coefficient, F1 score, and kappa of percent, and this evolutionary method can be used for real-time application to classify the sleep stages of persons using their real-time EEG data. We plan to use hyperparameters and transformation techniques using optimization techniques for improved performance in real-time application. In addition, the proposed method will be tested on other active biopotential signals. A comprehensive review of the movement imaginary brain-computer interface methods, challenges and future directions in motor imaginary, MI/BCI. The imagination of movement modifies the cortex brain activity. Such activities are then used in pattern recognition to identify certain movement classes. MI/BCI could be used to enhance the life quality of physically impaired subjects. Several challenges exist in MI/BCI, including selecting appropriate channels, usually linked with a suitable classifier choice. The entire procedure must be real-time in practical applications. A variety of channel selection and classification methods were used for MI/BCI in the literature. Also, hybrid machine learning, ML, and deep learning, DL, methods were used in the literature. In this chapter, different channel selection, ML and DL methods, validation frameworks, and performance indices of EEG-based methods were investigated. 322 papers published between January 2000 and March 2021 were analyzed in this systematic review. Specific challenges and future directions were then provided. Brain-computer interface, classification, deep learning, motor imaginary BCI, validation frameworks, introduction. Direct communication between the brain and an external device is known as a brain-computer interface, BCI. It is part of human-computer interaction, HCI, a discipline concerned with designing, implementing, and validating human interactive systems. 1. Since the first attempt of BCI by Vida in 1973, 2. Various methods have been proposed in the literature. Different neuroimaging signals were used for BCI, including functional magnetic resonance imaging, fMRI, 3. Magnetoencephalographic, MEG, 4. Electrocorticographic, 5. and electroencephalographic, EEG, 6. Signals. EEG signals are usually used for BCI due to the cost and their high time resolution. A typical EEG-based MI classification has 4 steps: FIG. Different steps of an EEG-based MI/BCI system. Reproduced with permission from N. Padfield, J. Zabalza, H. Zhao, V. Macero, J. Ron. EEG-based brain-computer interfaces using motor imagery, techniques and challenges, sensors, Basel, Switzerland, 2019. EEG-based BCI is further categorized into 2 groups: spontaneous, endogenous, and evoked, exogenous, EEG-based BCI systems, 7-8. Unlike the evoked EEG resulting from external neural stimulation, spontaneous EEG is generated based on specific mental activity. Motor imaginary, MI, BCI is an example of spontaneous BCI, in which a user imagines the limb's movement. In this chapter, we focused on the EEG-based MI methods, and the following issues were analyzed: sample size, number of output classes, input features, feature selection/reduction, machine learning (ML) methods, validation framework, and performance indices. PRISMA Guideline: the preferred reporting items for systematic reviews and meta-analyses. PRISMA statement was adopted in our study to select the relevant studies. 9. We searched the online database of PubMed between January 2000 and March 2021 using the following terms: motor imagery, or imagination of movement, or imaginary motor movements, or imaginary, or movement, and brain-computer interface, and classification. Peer-reviewed articles in English on humans were analyzed. The eligibility criteria were as follows: 1. Reporting at least an accuracy measure, and 2. Applying at least an ML method. Fig shows a flow diagram. Overall, 780 papers were screened, and finally, 322 papers were analyzed. Fig. Flow diagram of the study selection process. Reproduced with permission from D. Maher, A. Liberati, J. Tetzlaff, D. Altman. Preferred reporting items for systematic reviews and meta-analyses. The PRISMA statement, PLOS Med. 6, 2009, E100097. Results of 322 analyzed MIBCI methods, some benchmark BCI datasets, including BCI competitions, were frequently used. They were entitled as Dataset 110 in our study. The details are listed in table. The analyzed results of 322 MIBCI methods are listed in table. We focused on the sample size, the number of movement classes, features, input features, feature selection/reduction, ML methods, and their validation framework, performance indices. The acronyms used in table were provided as their footnote. Table: the benchmark datasets and their specifications. Dataset name: number of subjects, number of studies in table that used this database. Chapter 8, Dataset 10. BCI Competition 3 Dataset V, 334, 36 Table: the analyzed MIBCI methods. Reference method: sample size, number of output classes, input features, feature selection, feature reduction, ML method, validation framework, performance indices. Babyloni et al. Chapter 9, LDA. 10-10-fold CV epoch CV error rate equals 0%, and percent for each subject. Online error rate equals percent, and 14% for each subject. Furtscheller et al. Chapter 10, NA. Linear classifier holdout epoch CV accuracy equals percent, and percent for each subject. Roberts and Penny, 15, MIBCI plus mental imagery 7-2 AR coefficient. Chapter 11, LDA. 10-10-fold CV epoch CV classification error equals 5%, and 9% for each subject. Obermeyer et al., 17, MIBCI plus mental imagery 3-2, 5. Chapter 12, NA. KNN, 1NN, holdout epoch CV correctly classified equals percent, and percent for normal subjects in each session, and percent, and percent for abnormal subjects in each session. Cincotti et al. Chapter 13, NA. SVM FDA Adibus 10-10-fold CV epoch CV error rate equals percent, FDA, FDA, Adabust SVM, FDA, and 0% SVM, for each subject. Latte et al. Chapter 14, CC. Holdout epoch CV accuracy equals % and % for whole data and selected data, those trials in which the subject's intention was relatively strong. Banghua et al. Chapter 15, Na. VE Bayesian classifier holdout epoch CV accuracy equals above 30% for all subjects in the test set. Chance accuracy for 4 imagery classification was 25%. Furt-Scheller et al. Chapter 16, LDA. 10-10-fold CV epoch CV accuracy equals % and % for right hand versus left hand versus foot, and right hand versus foot. Wu et al. Chapter 17, Na. Shrinkage linear discriminate analysis classifier leave 1 out CV epoch CV kappa equals Daly et al. 109 MIBCI plus mental imagery 14 individuals with cerebral palsy 2 logarithmic band power features. Time period. Chapter 18, SVM. Holdout classification was repeated 100 times while mixing the sample order, and the average of these outcomes was the final classification rate accuracy equals % Park et al. Chapter 19, Na. Gaussian kernel-based SVM holdout, 10-fold CV for one subject, epoch CV accuracy equals % and % for one subject, dataset 9 and dataset 5. Vidor et al. Chapter 20, WSVM. Holdout, 5-fold CV in training, epoch CV accuracy equals 100% for best performance subject. U et al. 130, MIBCI plus P300 potential 6-2 CSP, P300 waves. Chapter 21, SVM. Holdout, 10-fold CV in training, epoch CV accuracy equals % for dataset 5 and dataset 9 and % for 13 subjects. On et al. 132, MIBCI plus SSSEP, from the TSA 16-2. Chapter 22, Na. The proposed structure combined KNN, LDA, and SVM algorithms into a decision tree structure. Holdout, leave 1 out CV in training, epoch CV accuracy equals % Bamdadian et al. Chapter 23, 3 miles, 2 ERP. ERP, spatial feature, signed square of the point biserial correlation coefficient, temporal feature MI, CSP ERP, for temporal feature selection. Between 4 and 7 temporal windows were automatically extracted using a heuristic search for peaks in the SGN R2 between targets and non-targets MI, optimizing spatial filters. Chapter 24, MIBCI. For subjects in minimally conscious state 2 automated selection of subject-specific frequency bands and neural time series prediction pre-processing using neural networks in conjunction with regularized CSP. Chapter 25, MIBCI. 15-4 peak of maximum negativity, mean amplitude, slope of a linear regression fitted to the data window. The average power in the interval from 0 to 5 Hz. That is the heart of artificial intelligence-based brain-computer interface. If it helped, a quick subscribe keeps more summaries coming. So how do classification and features connect? That is exactly where we started. Go back to the top and watch it click into place.